Hello everyone and welcome back to Vision Unleashed and Breakthroughs Shaping the Future of Computer Vision. I am Ramasaya, a researcher in Visual AI Systems, and today we are on episode 3, Bird Goes Visual, exploring masked autoencoders and how masked modeling transformed pre-training for vision models. As always, I am joined by my colleague and friend Dr. Sukant Khurana, vision scientist and neuroscientist extraordinaire. Great to have you here, sir.
Thank you, Ram. Excited to dive into MAE. This method really shook up how we think about learning from images.
Yeah, so let's kick off with the basic idea. In BERT for NLP, you mask random words and ask the network to predict them. So MAE does the same for images by hiding patches. How do you first react when you read the MAE paper or listened about the whole concept?
Yeah, so see, masked autoencoders were simply fascinating. The simplicity of randomly dropping 75% of an image patches felt extreme. In fact, rather insanely extreme at first. I thought you can, can you really hide three-quarters of a photo and still reconstruct it? But that very challenge forces the model to capture deep semantics, global shapes, textures, even object relationships. So it's extremely fascinating.
Exactly, sir. And MAE's design is asymmetric. Only the encoder sees the unmasked patches, while a lightweight decoder stitches everything back together. Why is that split so crucial, sir?
I would say efficiency. The encoder only processes 25% of the patches, so it's fast and memory light, right? So
Yes.
the decoder used only during pre-training handles reconstruction, but is small compared to encoder. After pre-training, you discard the decoder and keep just encoder as your feature extractor. So it's computationally very light and yet very powerful.
Exactly, sir. So that's a major use case of MAs. So basically, when I had experimented with MAs, primarily on some aerial drone footages, like hiding random 16 into 16 blocks across high resolution frames. So the model quickly learned to fill in missing roof edges and, tree canopies. So it felt like watching a jigsaw puzzle solver in action. So, like, what's your take on that, sir?
Yeah, exactly. The jigsaw puzzle analogy resonates. The more pieces you hide, the harder the puzzle. At 75% mask ratio, the network can't rely on local color and texture alone. It must infer the structure from context, like guessing the rest of elephant's body when you can only see the tusks and trunk.
Exactly, sir. So that's properly said. So let's talk numbers now, the figures. So a VAT based pre-trained with MAE on ImageNet 1K reached around approximately 83.6% top-on accuracy when fine-tuned over 2 points above a supervised VAT. And VAT huge hit nearly 88% top-on accuracy. So those gains speak volumes about the quality of the learned features and the quality of the method itself. Don't you think so, sir?
Yeah, they do absolutely. The linear probe experiments showed that these features are highly separable, meaning a simple classifier on frozen MAE embeddings outperform many supervised baselines. That was compelling evidence that MAE representations generalize very well.
Exactly, sir. And like, let's talk about the variants now. So, Sem MAE grabbed my attention first. So, how does semantic masking improve upon random masking, according to you, sir?
Sem MAE first segments an image into semantic parts, like wheels on cars or petals on flowers, using lightweight part discovery model. It then masks patches within those parts, so the model learns both local and relational cues. Instead of random holes, you get focused puzzles that teach the network to understand part composition. Instead of random holes, you get focused puzzles that teach the network to understand part composition.
Yes, sir. So, like, Talking about my personal experience, when I ran Sem MAE on medical ultrasounds, like masking regions around detected organs, so the model then produced reconstructions that highlighted organ boundaries beautifully, and downstream pathology classifiers saw a 1.5% boost in accuracy. So, don't you think that's a perfect example of how the Sem MAE works well with the downstream tasks?
Yeah, it's a fantastic real world win. And then there is then there is an approach of uniform masking for pyramid transformers like SWIN, which
Yes.
picks one patch per region to mask, preserving locally while still hiding a good portion of the image.
Yes, sir. And I also read about the SOUP MAE paper, so which mixes supervised labels into the pre-training loss. Does that blend self-supervision and labels really move the needle?
It does. SOAP MAE adds a classification head on visible patches during pre-training. So the encoder learns to predict labels alongside reconstructing masked regions, right? This dual objective yields features that transfer more robustly to new domains and often require less fine-tuning.
Yes, sir. And beyond image classification, MAE has further inspired applications in 3D and medical fields. So I saw a neat demo where MAE style masking was applied to neural radiance fields, masking slices of a scene and teaching the network to infer missing viewpoints. The reconstructions were like kind of striking, amazing.
Yes, yes, leveraging MAE in 3D pushes the envelope. Self-supervised 3D pre-training for novel view synthesis, and in medical imaging, MAE pre-trained on large unlabeled X-ray corpora yields encoders that detect anomalies with the minimum labeled examples, critical in healthcare where annotations are costly.
Yes, sir. Now, for researchers looking to try MAE, what tuning knobs matter the most, sir, according to you?
Start with mask ratio 75% is a proven default, but domains with structure textures might benefit from a 65% or even 85%. Keep the decoder small so pre-training always stays efficient. And
Absolutely.
visualize reconstructions early on. In your model, if your model can plausibly fill in the missing parts, say reconstructing a bird's wing or a building's facade, you know it's learning meaningful structure.
Exactly, sir. So that's a great advice from your side. And for compute efficiency, you can even combine MAE pre-training with mixed precision training and something like gradient checkpoints to handle large backbones. Right, sir?
Yeah, absolutely. And once you have pre-trained MAE encoder, adding lightweight task-specific head, whether for segmentation, detection, or classification, is trivial.
Yes, sir. So that modularity is gold, I think, sir. All right, Dr. Sukant Khurana, sir. So thank you for this enlightening discussion on Master to Encoders. Next episode in Vision Unleashed, in episode 4, we'll talk about DATR's decoding, where we'll see how transformers reimagined object detection without anchors or non-max separation.
Yeah, I'm really looking forward to it. Ram.
Thank you, sir, for tuning in. If you enjoyed today's conversation, please subscribe, like, and share. I'm Ramasaya signing off. See you in episode 4. Thank you.
Thank you.